In case you haven't seen it, I have these links to the recordings of these lectures. Your next task is to do these exercises. This is the second assignment called Basics. And there's a lot to do here, but there's small problems. But there's many small problems, okay? So here they are, and you're gonna wanna put some time into this. Hopefully you've already started this. So I just want to just sort of quickly scan through these and talk about some of the topics that need to be covered in order for you to do these assignments. But we are following this, this schedule here. But to do these assignments, I see that you need the information down to this point. So I haven't talked about this yet, but you can, of course, read about that. These are reading assignments. All right, let's take a look at this first one. Here's the first one. It says that you need to write a console program. All programs we write in this class are console programs. Well, maybe at the end we'll investigate a non-console program. And the program prompts the user for 3 double precision floating point values. And then the program displays the following things: the sum of x, y, and z, the sine of x, the cosine of x plus y divided by z, and so on. You need this header file for this program to work because that header file declares the existence of sine and cosine and log, which you'll need. Let's take a quick look just to get you started on this. We have a prompt. We need to display a prompt. And so I'll do something like enter a value for x. I have that in quotes because that's a string called a string literal. And then we need to read that in. We need it to, we ask that the user enter a value for x. Oops, I'm not a VI. I need to CD into the folder where this program is. Okay. I'm inside ex1.cpp under the basics folder. That's what you need to do for the assignment I'm talking about. You need to put your files in this basics folder. The files are named ex1 for exercise 1, ex2.cpp for exercise 2, and so on. So we're inside here. I'll use ls just to verify that what I'm looking at in this graphical display, in this tree view, is the same as what I see in the console window. We're looking at the same file system and the same folder in the file system. So let's go ahead and compile this ex1 program and run it. It says enter a value for x. That's our prompt. That's a prompt. And now let's read in the value for x. So we need, when we read the value in for x, we need to have a storage location in memory to store the value the user enters into the program. We're going to declare variable x as a double precision floating point value. So that's 8 bytes, almost always, that I've ever seen. And then we use the standard input stream. That's identified by CIN. That's the standard input stream. Just like Cout is the standard output stream. The standard output stream is connected to the terminal window by default. The standard input stream is connected to the keyboard by default. We can override that and connect it to some other input stream, such as a file. We connect it. When we run the program, we could tell the operating system to assign the standard input stream to the contents of a file, and the program would then process the contents of that file. So we use this input operator. Look, the arrows go the other way. Well, they're not arrows, right? They're less than symbols, 2 of them. Now these pointers are pointing in the other direction. So pull out of the input stream a floating point value x. And then let's use x. The value of x, the value of sine x is, and I'll just call the function sine x right there. Let's do a new line so we don't confuse the output with the prompt that comes up. So we have this standard output stream, the string, the value of x is, or sine of x is, another output operation, and then we call the function sine, pass in the variable x. Let's see what that does. Oh, sine was not declared in this scope. What's the problem? Great. Yeah, that's great. You're following that really nicely. Good. We need to include CMath. So it's a non-visible. We need to make the sine function exists in the system. We just have to make it visible to the compiler when it processes our code. All right, let's try that again. Silence, that's good. That's a success. Enter a value for x. All right, so let's see, the sine of 0 is 0, right? And the sine of pi is that 0 also, right? One, 4, 1, 5, 9, that's pi, right? So it should come out 0, close to 0, won't be exactly 0. The value of sine x is that number close to 0? It is. It's scientific notation. You see the e minus 0.6? So it's times 10 to the minus 6. So that's a really small number. That's 0. But we didn't get 0 exactly because this is not pi exactly, is it? Now, it's an issue in computing, is that we're trying to represent numbers that may have infinite decimal representations, like pi, or 1/3, etc. But we can't express those. Well, we can't express those. We don't express those normally. The way computers are built, those are not expressed as exact values. We specify them with approximate values, like this value here that I entered for pi. So when the calculations are done, we won't get exactly what we would get theoretically if we had assumed infinite computability. All right. So that's how to do. Now you just have to go through there and work these details out and do the whole problem. Okay, so you need to prompt for a y and a z, and then you need to do these other calculations. What about the second program? This has you practice with the if statement. Or prompt the user to enter a number between 3 and 12. If the user enters a number inside the interval 3, 12, the problem displays good number. Otherwise, the problem displays. This should be the program displays, right? Just to show you how convenient it is to use this system here. I'm using something called GitHub. If you turn into a programmer, you'll learn about GitHub pretty soon. It's used widely used these days by programmers. And so the program displays a good number. Otherwise, the program displays a bad number. All right, so let's modify. This should be ex2 now, right? So we're going to just go ahead and do that. We could copy the file from here. Now we could do file copy up here, somewhere in there. Maybe it's in there, copy. But you need to learn the command line version of these operations. So I recommend that you use the copy operation that you need to have memorized for the exam. So there's ex1. So you'll do that. Use CP. That's for copy. CP copy ex1 to ex2. There it is. You can see the tree version of this folder has just been updated. We can close ex1 and open ex2. So enter a value for x that is bigger than 5. All right. So we ask the user to enter a value of x that's bigger than 5. If they enter in a good number, we'll say good number. Otherwise, we'll say bad number. So we'll use an if statement for that. So if x is bigger than 5, it's greater than 5, then we're going to print good number. Otherwise, we're going to print bad number. We'll use an if-else statement. You see that? Here's the condition right there. I've highlighted. X greater than 5. So that's an expression. Expressions are either true or false. We don't know now if this expression is true or false because we don't know the value of x. We won't know the value of x until we run the program and the user enters a value for x. Then we'll know x. And when we know x, then the program will evaluate this expression, and the result will be true or false. If the result is true, we'll print good number. Otherwise, we'll print bad number. And this is the syntax for this type of logic. Enter a value for x that is bigger than 5. So I'll do 6. Good number. Let's run it again. We don't have to compile it again. It's already compiled. Enter a value for x that is bigger than 5. Well, 3. Bad number. So we got it working. Now, I didn't solve the problem that you need to solve. You need to solve a problem that's similar, right? You have to check to see if something is inside an interval. You want to check to see that x is greater than 3 or equal to 3 and less than or equal to 12. So you'll need to use an expression that uses a Boolean operation. Let me show you that. So we want that x is greater than 5 and x is less than, say, 10, right? This is solving the problem, the following problem. Enter a value for x that is in 5, 10. You see, I use the math notation here. In math, you use parentheses to exclude the endpoints of the interval. But in the problem statement, I'm using square brackets to indicate the inclusion of the endpoints 3 and 12. And so that's consistent. My descriptions here are consistent with math notation. Enter a value for x that is in the interval 5, 10. And I'm going to put a space right there because I'm a stickler for accuracy here. And so did I get that right? It's strictly greater than 5. If it was going to be in the interval, 5, 10 like this, right? Then I would do greater than or equal to 5 here. Let's do it like that. We'll be in this interval that includes 5, goes up to 10, but doesn't include 10. Let's do that. So it means this expression should be x must be greater than or equal to 5, and x is less than 10. So I put a 5 in there. What should it be? Is it a good number? Good number. Did I put in a 10? Is that a good number? No. Bad number. So we're testing it now, see? So 7 is a good number. We're testing it. 2 is a bad number. -1 is a bad number. There we go. That's exercise 2. What about exercise 3, looping? Write a program that prints every number between 330 and 550, inclusive, but to print every number. So you got to print numbers in an interval. I should say print every integer, not every number, right? Not very, I'll fix that right there. I should be precise. I want you to be precise. I should be precise too. Every integer. Because number is kind of a general term. It's not specific. We don't know what kind of a number are you talking about. Right? All right. So let's do that one. And I'm going to copy this file again. You can see it pops up there. And all right, so we don't need this. We don't need this. We got to print a bunch of numbers. Let's print integers from 4 to 44, inclusive. By inclusive, I mean including 4 and 44. So we use a loop. First, I'll write it in pseudocode. For I equals 4 to 44. Maybe I'll do it like this. It'll look something like this. Like do for, I don't know how you want to say it there, do for this. It's a loop, repeat, maybe repeat for. Repeat for I equaling 4 to 44. And we just want to print the value, that's it. We don't want the values to be, stuck together, so we'll put a space there, okay. And we normally have braces, although this is not valid syntax. So we want to repeat something over and over again. We want this variable I. You know what? Let me do it. I'm going to do it two ways here. So we have an integer variable I, and we'll initialize it to 4. Okay? And then we want to execute a block of statements while I is less than or equal to 44. We'll print I. And then we increment I. So we need to increment I. So there's the loop right there. Create a variable I, initialize it to 4. That's the first value we want to print. So we print 4. Then we increment I. This is the increment operator. So now I transitions from 4 to 5. And then we keep printing. So now we're going to print 5. Then we increment. I becomes 6. We print I. We print 6. And then we increment I, and so on. Now we repeat this block of statements. Here's the block right there between these braces. That's called a statement block. We're going to repeat this block of statements as long as I is less than or equal to 44. What happens when I equals 44? Well, we do this, right? Because 44 is less than or equal to 44. But then when we increment I and I becomes 45, what do we do? Well, let me tell you that this thing that I've highlighted right there is one statement. You should see this as one statement. Well, you can see it as one statement, and you can see it as multiple statements, both. These are called substatements. So it's a compound statement. And the program will run this statement first. That's the first statement in the program. Then it will run this statement. That's the next statement in the program. And when it finishes this statement, which is a complicated statement, it does something over and over again. But when the loop condition becomes false, the statement terminates. And execution moves to the next statement. The next statement, the third statement in the program, the third top level statement, we'll say, is that statement, see out done. So I want you to be very clear about this. I'm trying to go slowly and carefully here. I want you to see the relationship between statements and substatements. And that the code will run in a linear manner, usually. But then we have ways of breaking that linear execution. One way of doing something other than straight linear processing is to use a loop. This is called a while loop. There's other types of loops. Another way to break the normal sequential processing of statements is to call a function, to move a block of code into a function. It's like a named block. A function is a named block of code that takes input variables. So you can branch to this block of statements that's in a named function, execute those, return back to your original place, and then carry on from there in a sequential manner. All right, let's see if this works. It's always good to check out your code. Let's see, CPP. It should print the numbers 4 to 44, and it does that, and then done at the end. This is very important. This is what you're going to be doing pretty much for the whole quarter. Very little else. Most of this has to do with looping, and then there's if statements. So you've seen the basic material and techniques that you'll need through this quarter. In fact, for all programming, this is how algorithms are implemented. You need loops. You need conditionals for branching. we'll look at some other techniques later on, such as functions and classes, but this is the core. You don't need functions. You don't need classes. Without these advanced features that help with organizing your code, what I've shown you right here is sufficient to write any program. Loops and conditionals. You don't need functions. You don't need classes. You don't need lots of stuff. But all of that additional technique that we'll be learning just helps to make the code more manageable as a human, not for the computer. A computer has a very primitive set of operations. The problem is taking complicated programs and translating them into these primitive operations that the computer can carry out. So a lot of what we're learning is techniques to improve the sort of the reasoning ability of the programmer to specify programs. And there was a question back there.
What is the return zero stand for?
Say it again.
There's a return zero in line number 7.
Oh, it returns 0 because main returns 0.
Okay.
Main returns an int.
Okay, so basically it stops the program?
Well, this is, you can return other things. You can return -1. Let me show you that. It looks exactly the same, doesn't it? But actually, when the program runs, if another program launches this program, it may look at this return value. By convention, we return a 0 to say everything worked okay. And we return a non-zero value, -1 for instance, or 2, whatever, something that's non-zero, that's an indication that something went wrong. And the value we return may be an error code, or it may just be non-zero. So when you write, as a system administrator, when you write scripts, you can check for the return values of programs and decide whether to carry on and run the next program. Because maybe you have a sequence of programs that you're running, you might just stop and say, oh, something went wrong, let me report the error to the system administrator, and then that's it. Got that? It's a little tricky. But actually, you don't need this to compile, because the compiler will add a return 0 operation for you automatically. But that's only in, well, maybe it's in other functions too. So there is, see, no problem. But it is returning 0. Yeah, question back there.
Where is it returning 0 to?
It's returning 0 to the program that invoked it. What program invoked? What program is invoking a.out here? The command line interpreter, or the console program, the terminal program, whatever you want to call it. And that's part of the operating system. See, you can run this program up here too. I've never done this, but I think I can do this. Let's see, maybe I got to do like run. Run with, I think it is trying to compile it, something like that. Anyway, it's returning the value to the program that ran it. I'll give you another, let me see if I can come up with an example. Maybe we create a new file here, and we'll call it run.sh, sh for shell. And run will run a.out. And I said, I don't do this enough to remember. How do we get the return value from a function? So here we have a shell program. This is a script program that is running a.out. So here's run.sh. You see a.out? These are called the permissions. This is the owner permissions. This is the group permissions. And these three characters represent the permissions for all users in the system. I don't want to go into detail here. You know, this is a system administration issue. Unix-based operating systems look like this. Windows does not operate like this. Mac and Linux operate like this, and other Unix systems, like Android, right? That's our Unix system. So this run.sh doesn't have that X character. You see the X up there? So it's not executable. They need to make it executable. And this is a command that does that. And I use that -L argument to produce a long list. Now you can see I made run.sh executable. There's the X. Now we can run that. And so run is a script that just calls a.out. But how do we get the return value? Do I echo it? I don't remember. I'm going to play around for a second. No, that's not it. How do I use the return value? Watch this. This is a technique that you see in scripts. I'm going to play with this for a sec. Am I returning 0? I am. See, look, it ran it twice. Let me try this. Maybe I'm getting off on a tangent. It's fun to go off on tangents, right? But I probably don't want to hack around too much here. So if I return a 1, what do I do? If I return a 1, so now it runs twice. If I return a 1, wait a minute, that's not right. You know what? I don't want to get into this. Sorry, I'm going to get lost there. We'd have to take 15 minutes, 20 minutes. I'd have to research on the web. All right, so let's skip that. All right, so that's that one. Oh, no. I want to show you a different form of the loop. This is a while loop, but we can use a more compact syntax called a for loop for this. And it looks like this. For integer I equals 4, I less than or equal to 44 plus I. All right, so I'm going to comment this out. I'm going to use a multi-line comment. See that? You see the editor is nice. It turns all of that to green. So these two loops are equivalent. This is called a while loop. This is called a for loop. These two loops do the same thing. The for loop is just a reorganization of the code. It's got inside this line right here, you've got an initialization section. That's the thing that you want to do, the operation you want to perform before entering the loop. So you can say, I just moved that declaration and initialization of I into this first section of the for loop. Then there's a semicolon that ends the first section. And then the second section is the loop condition. See, the loop condition is up here. That's the thing that's tested each time you execute the loop, each time you go to execute the loop. the system evaluates the loop condition. If the loop condition is true, we execute the statement block. If the loop condition is false, we terminate the loop statement. We go on to the next statement in the program. And the third section is the end of loop operation. It's the thing you do after you've executed the statement block. After you've run all the substatements, then you do this operation, you increment I. That's why I had it down here, see? Now the order is important. I have to do this after printing I. If I incremented I before printing I, I would get the numbers 5 to 45, right? Well, I think so. I would get 5 to 40. If I did this, the order matters here. I'll print 5 to 45, but I want to print 4 to 44. Anyway, we know here that this operation is at the end of loop. I want to test that. Let's test this loop here to see if we get the same result. There it is, same result. So this is the for loop. Now that's the loops and if statements are part of flow control. Let's take a look at my notes here. And they have something called a range-based for loop, and I never use this. So I'm trying to learn new things. This technique here requires the newer version of C++. Let's see that. So we declare a string S. This is it. And then we loop through S. And we basically examine each character in the string. And this is one way to do it. Let's see if this compiles without the special argument to change the version of the language. So it's complaining. Range-based for loops are not allowed in C++ 98. That must be the version we're using. Let's use, that's std, C++ 11. Now it's okay. And you can see it prints this is it right there. Because we're pulling out one character after another. To see it in the older version, let's take a look at that syntax. So this will be for integer I equals 0. I is less than s.size plus plus I. And we're going to print s of I. This is how you would do, now let me do it like this. There's the new version. Because the old version works with the new compiler, so this is how you would do it with the compiler that's used by default. The string S is a sequence of characters. Each character has a position. The first character, this uppercase T, that's a position 0. The first position is position 0. It's a little confusing. The first position is position 0. And then, so what we want I to start at 0. So I is the position. It's a variable that represents the position of some character in the string S. So we can access the character at position I using this notation. So S square bracket I. Now, we start at 0, but how far do we want to go? We want to go to S dot size. So if the first position is 0, and this is position 0, then what's this last position here? Let me count it here. So the T is a 0, H is 1, 2, 3, 4. That blank is position 4. 5, 6, 7. That's another blank. The second blank is at position 7. 8, 9, 10. So we want to print the characters at position 0 through position 10. What's the size of S? What is the size of S?
11.
Size of S, that's how many characters are there. If you label the characters 0, 1, 2, 3 to 10, how many labels do you have? 11. If you start labeling at 1, then you'll get 10 characters. You'll get 10 labels. But we're starting labeling at 0. This is an instance of the one-off problem in computer science. And you see this problem everywhere. It's called the one-off problem. And you see it in different variations all over the place. So you always have to slow up and do some extra careful reasoning to make sure that you're not one-off. So the size of this string is 11. Now, what's the last index I? What's the last value for I that we want to use in this expression? We want to use I equals 0. That gives us the uppercase T. We want to use I1. That gives us the H in this. And we want to use I equal to 10. That gives us the period, right? But we do not want to use I equal to 11. Because that's a label that doesn't label anything. It's the size of the string, but it's not a valid label. It doesn't label. It's not a position where any character exists at. That's the reason I have strictly less than here. So we want I to be strictly less than 11. That means I can hit 10. It's okay. If I hits 10, we execute the statement block and print S of 10. And then when we execute the end of line operation, plus I becomes 11. And then when we check the loop condition, we have the expression 11 less than 11. Is 11 strictly less than 11? No. So now the loop condition is false, which means we've finished executing the loop statement. Now, we don't need this. We don't need the newer version of the compiler, so I can take that out. Let's see if we get the same result. There it is. There's the period. There's the uppercase T. We got it. What happens if we did something like this? I do recommend you try to break your code and see what happens. What happens if we go past the end of the string? What do we get?
It'll crash.
Huh?
Will it crash?
It tries to print a 0 to the console. And I don't know what a console will, how the console will render a 0. Because in memory, actually, this will branch into memory. I know the way strings are implemented internally. There's a byte with set to 0 at the end of the string at position. There's actually a position 11 that's hidden from us. And at that position, it's a byte with value set to 0. So we're going to send a 0 to C out. The character 0. I don't know what it's going to do. Oh, it just shows a blank, see? Right there. So what we're doing there is we're not printing, we're doing this. We're printing the 0 character. That's what we're printing. We're not printing a 0. That's different. If we print a 0, that'll be rendered as a 0. This is different. We're telling the output stream we want to interpret the 0 as a character value. Here we're telling the output stream, oh, print the number 0 for us, not the character represented by 0. This expression is the character represented by 0, and there is no character represented by 0. There's a character represented by other things like say 50, right? That's probably something. How do I do 50? I'm going to try to remember this. Is it x50, 0x? I think that's it. This is a hexadecimal 50. Let's see what happens. Oops. Multi-character constant. So how do I print? Maybe it's this. Oh, a left parenthesis. So this is a hexadecimal notation. 50 is for left parenthesis. Oh, what do you think? Right parenthesis. I'll bet that's at 51, right? Let's try it. It is. So anyway, this is important. You know, you'll work with that later on. By the way, I'm covering some topics in constants here, also in operators, and basic input and output. Basically, I'm covering topics in all of these sections right now. So we looked at looping. What about the modulo operator? Let's see what the exercise asks you to do. Write a program that prompts the user for an integer. So we know how to do that. The program reads the integer and displays even number if the number is even, or odd number if the number is odd. So a number is even if it's evenly divisible by 2. So the way we solve this problem is we use the operator. And let's go ahead and look at that. So if I have a variable, let's do it like this. Let's read the value k. So integer k, let's read in k, and they're going to print k mod 3, and then a new line. you see that? This is the modulo operator. That means divide k by 3 and report the remainder. So 4, for instance. What's 4 mod 3? Take 4 and divide by 3, you get 1 with the remainder of 1. So this expression evaluates to 1 when k is 4. What about if k is 7? If k is 7, 7 mod 3, so 7 divided by 3 is 2 and 1 remainder. So this expression evaluates to 1 also. So when k is 4 or when k is 7, this expression evaluates to 1. This is the modulo operator. So if you're advanced in your math program, I'm sure that you've looked at the modulo operator. It's an important operation in math and in computer science as well. It's used quite a bit. So it's an important concept to be familiar with both of those two areas of interest, mathematics and computer science. Let's look at 4. So it's waiting for a number. I'll pass in a 7. So this should evaluate to 1. There it is. How about 8? 8 should evaluate to 2, right? So I take out 2 3s and I'm left with 1 with 2. And what about 9? 9 mod 3. Well, 3 goes evenly into 9. So the remainder will be 0. There it is. Now, how would you test for an even number? Mod 2, right? Okay, so I'm going to leave it with you there. You do mod 2. What about this exercise 5? We already looked at an if-else statement, didn't we? So let's skip that. About exercise 6, random numbers. Write a program that generates a list of 100 random integers. The standard library contains a pseudo-random number generator. And that pseudo-random number generator is in this, declared in this header file. Let's take a look at that. C standard lib. Inside there is a function called rand. I can call rand. The function rand returns the value x. The function rand returns a value x, and then we can print x. Yeah, I didn't change the number on this, but you'll need to do that. Here's a random number. 1.8 and so on times 10 to the 9th. It's called a pseudo-random number generator. It's not a true random number. True random numbers don't have cycles, but rand, the function rand, has a cycle. At some point, the values returned by rand repeat themselves. By the way, random numbers are essential for encryption. If you use rand to do an encryption, then you're going to get hacked. You have to have something that's stronger, a stronger pseudo-random number generator. You can't get a true random number generator, like just in code. But the random number generator would have to access information like something that's more random. Yeah.
I just ran that program on my terminal as well, and I got the exact same number.
Yeah. I'm going to talk about that now. Good observation. I'm going to run this again, right? I get the same number over and over again, right? That's because it's using the same seed. The pseudo-random number generator is just some code that runs. And every time you run it, the same code runs. But it uses a seed. And you can change the seed using this function srand. You're telling the system that, use 0 as a seed. So now when I run it, I get the same number. That's because 0 is the default seed. Let's change the seed to 1. Now I should get a different number, but I don't. Are we getting the same number? What's going on? Maybe if I make that a 2.
Did it make a zero?
I got it. It's different now, right? Now it's different. It's kind of inconvenient to get this information here. What if I make a 3? I get something different. So it's the seed. And by the way, let's use a loop to print 4 random numbers. Because your program asks, the assignment asks you to print something over and over again, 100 random numbers. Here's a loop that prints 4 random numbers. There's 4 random numbers. The 4 numbers are different. Like every time we run it, we're going to get the same list because the seed is the same. See, it's the same sequence of numbers. So we have to change the seed each time we run it if we want a different sequence. The standard trick, if you don't care about security, you're not using this for security purposes. If you're using it for something like a video game, it's all right to use a weak random number generator. So what we do is we pass in something variable, like this is the number of seconds that have elapsed since some epoch. An epoch means a point in time. Usually it's 1970, the first second of 1970, Greenwich Mean Time, something like that. So now when we run it, actually this might not compile. It does compile. Now look at what happens. I run it once, but the seed, they're passing in the number of seconds elapsed since 1970. It's going to be different now because it's been longer than a second. So we get a different sequence. Now, the numbers are kind of big, and they're displayed with scientific notation. We could specify some. There's a way to tell the output operator to avoid scientific notation, but let's make the numbers smaller. What we'll do there is we'll use mod. We'll do mod 100. Now, what's that going to do? X is no longer set to a big integer anymore. Now it's set to a big integer mod 100. Can you visualize the result? Huh? The values will be less than 100, right? They'll be from 0 to 99. My hearing's not good. I'm sure someone said the right answer back there somewhere. So now we're under 100. So this is convenient to use the modulo operator to shrink the set of random values that you're generating. I think we're near the end here. So this is that one. And is there anything else I need to say there? Yeah, I show that here, right? That's it. Next time, we'll carry on from there. That's it for today.